All right, implicit differentiation 2.5. Well, we know we're deriving because this is differentiation, but what does implicit mean? Okay. Well, we've worked with only explicit functions right now. And that would be something like, there we go. That'd be something like f of x equals, say, 2x plus 3. That's a function that's explicitly written in terms of x or y or something. So this would be another explicit function or explicit equation. We just take the derivative, like we took the derivative of this one right here, d dx. And if we took, I'll just put d dx in the back here in my room, that would be dy dx, right? And that would be what, 3? Okay. You guys know what an implicit function is, or an implicit equation? Well, it's one that's just not explicitly written in terms of y, or f of x. Say 2x plus 3y minus 7 equals 4x plus xy. It's not explicitly written in terms of, say, f of x or y. This is an implicit equation. We need another way to derive this. That's what we're going to learn today. Guidelines. Step-by-step process. We'll start with that today instead of going over one or two examples and then giving you the guidelines. For implicit differentiation, differentiate both sides of the equation with respect to x. For now, we're just going to differentiate with respect to x. So take d dx of both sides in layman's terms. Step 2. After you take the derivative of both sides, collect all the terms involving dy dx on one side. Could be the left side, could be the right side, but in here we say left side. Move all the other terms to the other side. Step 2, I just say collect dy dx. Step 3, factor out dy dx. Now, Ms. Bowling, what if there is a product? What if there's a quotient? What if there's this or that, the other thing? You still have to use those rules. Are we good? All right. All right, here we go. Find dy dx given that y cubed plus y squared minus 5y minus x squared equals -4. Well, step 1. Take d dx on both sides. All right, let's do this. We've only taken the derivative of y when it's been by itself, right? And we've always gotten dy dx. Now there's a problem here. We have y cubed. What would be the derivative of y cubed, do you think? Okay, 3y squared. That is what the derivative of y would be with respect to y. But we're taking the derivative with respect to x. So the variables don't agree. So think about this. When we took d dx of y before, we always got dy dx. It actually is 1 times dy dx. we actually took the derivative of y, which is just 1, right? And then we had to multiply by dy dx. Why? Variables didn't agree. We didn't go over that before. We just kind of showed you, right? But now the derivative of y with respect to x, or I should say y cubed, with respect to x, is 3y squared, like you think would happen. But because the variables don't agree, times dy over dx. Plus. Now let's take the derivative of y squared. Well, what's the derivative of y squared? 2y to the first power, right? Now, because we're taking the derivative of y with respect to x, dy dx. And you guys know what? This is kind of like the chain rule. It's kind of the chain rule because the variables don't agree. Minus. Okay, what's the derivative of 5y? Just 5, right? But we're taking the derivative of a variable y with respect to x, so we need the chain rule part of dy dx. Minus 2x. Now think about this for a second. I could have done this, and some teachers showed this a long time ago. I don't know if we really need it. Well, what's the derivative of x with respect to x? Dx dx. What's dx dx? That's just 1. That's why we never do that. Okay? And because the variables agree. We've just never done that. Okay, what's the derivative of negative 4 with respect to x? Or with respect to any variable? 0. Okay, that's step 1. So the only new thing we learned today is that if you take the derivative of a variable with respect to a different variable, you need that chain rule part of the derivative of that variable with respect to x or t or whatever we have down here. That's the only thing we're learning new today, guys. Okay, so there is the derivative, but we need to solve for dy over dx and get it written in a proper form so we can maybe find the second derivative. Okay, so step 2 would be to collect your dy dx terms, right? Well, all 3 of these have a dy dx on this side, so I'll keep these on the left side. And that equals 2x, right? If we move the terms that do not have dy dx to the other side. Step 3 would be factoring, correct? So we're going to factor out dy dx from all 3 of these terms. Okay, and then step 4 would be just solving for dy dx, right? And if you factor out, this is always going to be a product, so you're always going to be dividing. So then dy dx, the derivative of y with respect to x equals 2x over 3y squared plus 2y minus 5. Now before, all of our derivatives were only in terms of x, right? The change in y was only in terms of x. But now the change in y with respect to the change in x is in terms of x and y. So we need both an x and a y to find the slope of the tangent line to some curve. Yeah. You good?
Yes.
All right. One thing to speed this up. Right here, a lot of people, when they're at this part right here, mathematically they skip to this step and they say, okay, all 3 of these will be here on the left side. They factor out dy dx and they move something over. So they kind of skip this step, step 2. But for us, I don't think we should do that yet until we're really comfortable with all the algebra and the derivatives. Okay, so there's your derivative. All right, here we go. Determine the slope of a tangent line. Well, it's nice. The nice thing about calculus is we know what the slope of a tangent line is. It's a derivative evaluated at x value. Well, now we might need an x and a y value. Okay, so we show you guys something new, and then you use the same old ideas with this new technique of finding the derivative. Okay. X squared plus 4y squared equals 4. What's that the equation of? It's like an ellipse, not a circle, because the y would be stretched out. More like an ellipse or something, right? Okay, so at the point, well, that's nice. They gave us an x and a y, so we have to find an x or a y if they give us the other one. Okay. Well, let's write down our equation. Let's find the derivative, because the slope of the tangent line is the derivative evaluated at x, y. So let's find d dx both sides. Step 1. This would be proper work showing right now. Okay. Now we find the derivative. Now we just have to be careful of the respect to variable and the variable we're taking the derivative of. Okay. So we'll take the derivative of, with respect to x, x squared, 2x, just normal, right? Okay. Plus the derivative of 4y squared with respect to x. 8y, then dy dx, right? Equals 0. Okay, step 2 was isolating the terms of dy dx, right? So we'll move the 2x over. 8y dy dx equals negative 2x. And then it's already factored, basically. So let's divide by 8y. Negative 2x over 8y, which simplifies, obviously, to, would that be negative x over 4y? There's our derivative. Okay, that would be the slope for all tangent lines around that oval, okay, around that ellipse. In particular, though, this point root 2, negative 1 over root 2 is on that ellipse. What's the slope of the tangent line at this value? Okay, so check this out. Some new notation. dy dx. I'll put a line here. That means evaluate at root 2, negative 1 root 2. Equal sign. Okay. That's the derivative evaluated at a point. Because the notation is like, well, dy dx evaluated at what? So we're saying what we're evaluating is at. Okay, x is root 2. Y is negative 1 over root 2. A little bit of a mess. Let's clean it up. Complex fraction. So would it be negative root 2 over negative 4 over root 2 multiplied by the reciprocal times, would that be root 2 over negative 4? Negative divided by negative is a positive. Root 2 times root 2 is 2. And 4 on the bottom. And then we get 1/2. So slope of the tangent line at the point root 2 negative 1 over root 2 is 1/2. You guys can see how we could easily go to writing the equation of that tangent line now too, right? Here's your slope, here's your point, write it out pretty quick. Any questions on this? The derivative is just a little more complex now. That's all. Determine the slope of the graph of, again, now there's some more complex equation we need to find the derivative of. It's a good idea while you're writing things out, when you're reading the stem, kind of analyze the equation, point out some things you need to be aware of. Do we have a composite function where we need the chain rule? Do we have any products anywhere that we need to make sure we take care of with the product rule? Do we need the quotient rule anywhere? Do we need to rewrite? All those things you got to keep in mind, okay? All right, we need slope, so we need the derivative. Take the derivative of both sides. d dx All right, the left side has definitely a composite function with a constant multiplier of 3 out in the middle on the front. So derivative of outer function looks like 6 times, or at, the inner function. That'd be to the 1 power, right? Times the derivative of the inside now. The inner function with respect to x. Okay, derivative of x squared would be 2x. Derivative of y squared. Yeah, dy dx. Variables do not agree, so it's basically a chain rule or implicit differentiation. Equals. All right, right side. 100xy. That's a product, definitely. We need product rule. Okay. They're going to sneak these little variable stackings in all these problems, and you'll forget the product rule. All right, I'm going to take the 100 with the x. Because I don't want to have 100 and parentheses and stuff like that, okay? So I'm going to keep the 100 with the x. So first, 100x times derivative of second. 1 dy dx, right? Or just dy dx. Plus second, which is y, times derivative of first, which is 100. All right, what are we going to do here? We have to collect the terms of dy dx on one side. Problem is, we have a product here. So if we divide both sides by these two terms, well, now this guy is mixed up with a quotient. So guess what, folks? We actually have to distribute here and get this guy out of the product. Okay? So that we can collect variables by adding and subtracting on both sides and then factor. Okay, let's do that. I'm going to bring this 6. So I'll make this 6x squared plus 6y squared. Is that cool? Okay. So, and then we're going to multiply through, we're going to distribute. So 6x squared times 2x. 12x cubed. 6x squared times 2y dy dx. 12 x squared y dy dx. That's gross. All right. 6y squared times 2x. That'll be 12xy squared. 6y squared times 2y dy dx. Is that 12y cubed dy dx? A little bit of algebra 2 on steroids. Equals 100x dy dx plus 100y. All right, now we got to collect all the terms of dy dx on one side. So this one stays, this one stays, this one comes over, this goes over, this goes over. That makes sense? All right, 12x squared y dy dx, that stays. We got 12y cubed dy dx, that stays. Let's bring the other one over. Minus 100x dy dx equals, okay, 100y stays on this side. We got to bring the 12x cubed over, so negative 12x cubed. And then negative 12xy squared. Okay, are we good so far on that? Collect the terms of x, dx or dy dx on one side. Everything else goes the other side. It's just more convenient writing things left and right. Okay, factor. (12x squared y, 12y cubed, 100x. Notice we could factor out a common factor with these terms, right? We could do that if we wanted to. We will in a minute. Divide this quantity over. This is kind of where we need some soft jazz music playing. There we go. Well, if 4 is a common factor of all of this and all of this, we should be able to take care of this pretty easily. 100 divided by 4 is what, 25? 12 divided by 4 is 3. And again, 3. And then 12 divided by 4 is 3. 3 again. And then minus 25x. Guess what, folks? That's just the derivative. And they want us to find slope at 3, 1. All right, let's extend this page and do some more work. All right, dy dx evaluated at 3, 1, right? X is 3, y is 1. So that's a 25 minus 3 times, I'm just going to write 3 cubed. 3 times 3 times 1 squared. 3 times 3 squared times 1 plus 3 times 1 cubed minus 3 times 3. Let me know when you get something for the numerator or the denominator. Anybody else get negative 65 in the numerator? Yeah? Okay. How about the denominator? 9? Confirmation? No. What do you guys get? 12 in the denominator? Anybody else? You got 21? All right, we got what, 9, 12, 21? What do we, you got 21? 21? Did we forget our plus 3 right there? Or plus whatever? We get. Oh, yeah, that'll do it. Are we okay with 21 here? Yeah. All right. Cool. So we found our derivative. We've what? Right here? Did I write 3? Oh my gosh, did I write something wrong? Okay, 3 squared, 3 times 1 minus 25 times 3. It should be 25 times 3, right? Well, stop me earlier. Okay, now what is it? Negative 45? Well, that simplifies. Is that better? All right, good stuff. Okay, good deal. What's up?
13/9 is so gross.
Yeah. All right. Well, I wanted us to find the derivative and isolate dy dx. However, it just said determine the slope, right? Fun fact. We could have found the derivative, which is like right here, right? Yeah? We could have just substituted 3 and 1 right here. And then solve for dy dx if we wanted to. Okay? And the nice thing about that is, well, you have a number. Well, this turns into a number. Then you have a number here, a number times dy dx. So you're going to have just this number to distribute to these two items, right? Over here, you have a number times dy dx, and then a number. Distribute, and you'll have two items over here. Then you have two terms to collect over on the other side. Dy dx equals, then you get a number over here. Okay? So we could have done that in the future. It's okay if you do it every once in a while, but I'm going to have you guys solving for dy dx anyways. I'm going to say find dy dx and then find the slope. So we need to be proficient at doing this, which requires a little bit of algebra skills, right? Okay. Find second derivative. Evaluate the first and second derivatives at the point -3, 4. All right, we got x squared plus y squared equals 25. What type of graph would that show? That'd be a circle with what radius? 5. Okay. Circle with radius 5. So if we had a circle with a radius 5, we know we can find the slope of the tangent lines of that circle at any point on the graph. Okay, it has to be on the graph of that circle. You can't find the slope of the tangent line at like 724 or something like that. That's not on the graph. How would you do that? Okay. So obviously it changes. Okay, slopes of the tangent line changes, and there's going to be two spots where the slopes are the same. Okay. Second derivative, well, that would be acceleration, right? Let's find the first derivative. D dx. Okay, derivative with respect to x of x squared would be 2x. The derivative with respect to x of y squared would be 2y, then dy dx. Derivative of 25, 0. Okay. Solve for dy dx. Divide by 2y. And what would that be? Negative 2x over 2y, which is just negative x over y, which is not too bad. Well, Mr. Bonley, is that going to be the same derivative for all circles? Yep. Because the only difference is the radius, right? And that always goes to 0. Yeah.
I forget. Are you changing the position of a circle on the graph?
Like H, I believe they called it a lot of times. K right here. Where HK is the center of the circle. Okay. Obviously, that would create the chain rule. Right? Which wouldn't be too bad because they're linear with coefficients 1, so that would be too bad. All right. Well, there's your first derivative. It says evaluate the first and second at that point. Well, let's evaluate the first at this point while we're here. Dy dx, which stands for the first derivative, evaluated at the point -3, 4. Written in ordered pair notation. So it'd be what? -3 over 4, which is just 3/4. All right, so that would be the slope of the tangent line negative 3, 4 right here. 3, 4 is positive slope, right? I just find the second derivative. That means taking the derivative of the first derivative. So we're going to find d dx of dy dx, and then d dx of negative x over y. All right, what's the derivative of the first derivative? The second derivative. So it would be d squared y over dx squared. Now the derivative of negative x over y, that's a quotient. So let's find the derivative of this quotient. All right, low, which is y, d high, negative 1, again with respect to x, minus high, negative x, d low, derivative of y with respect to x. Say again, dy dx. And be 1 dy dx, obviously. All over, low squared. All right, well, we can organize this a little bit better. That'd be negative y plus x dy dx over y squared. Well, we have a problem. What is that problem? We have a major malfunction. What's the problem with the derivative, the second derivative? Well, here's the nice thing. We have the second derivative isolated on this side. But what's the problem over here? We have the first derivative inside the second derivative, right? That's part of the answer. Man, I wish we knew what the first derivative was. Substitute it in. What is the first derivative? Negative x over y, right? Over y squared. Well, that creates a little bit of a havoc because now we have a complex fraction, right? So we got to take care of this business. Negative y, will that be minus x squared over y now? All over y squared. Well, look at us. We're going to be combining some fractions, common denominator. So we need a y over y here, right? So that'd be negative y squared minus x squared all over y then. All over y squared. Multiply by the reciprocal, and we get negative y squared minus x squared over y cubed. So this is over 1, right? Multiply reciprocal, 1 over y squared. There, my friends, is our second derivative. We're not done yet, though. Evaluate this second derivative at the point. A little sloppy with my y there, my bad. Evaluate it at, man, this was so long ago. What was that point? Negative 3, 4? So it'll be negative 4 squared minus negative 3 squared all over 4 cubed. Negative 16. Is that minus 9 then? 64?